Hello, my name is Harry Duque. I am a verification engineer working at Access Communications in Sweden, and I am here today to share with you how we approach a particular challenge in constrained random verification. But first, I will talk a bit about trees. Here's a picture of an old oak tree near the village where I live in Sweden. It's called the klätterträd by the local children, which means the climbing tree. The reasons for the name are obvious. It was middle of the winter when I took this picture, so the tree is a bit bare, but it does help us appreciate the familiar branching pattern which is so characteristic of trees. Well, I'm not here really to talk about plants. Today we will talk about a different kind of tree, one which is inspired after a climbing tree here. I'm referring to a directed rooted tree, or DRT, which is a type of graph used in graph theory to model certain kind of pairwise relationships. In general, a graph is composed of vertices joined together by edges. A DRT is then a graph with the following characteristics. It is connected. Every vertex in the graph is connected to another vertex through an edge. It is oriented. Edges link vertices in only one direction. There is a kind of flow in the connectivity. It is acyclic. There are no cycles in the connectivity. You can only traverse a vertex once. Each vertex has a single parent. There is a single start point, a root, from which all other vertices point away. In the example to the right, you can see a simple DRT where the root is colored white. All end vertices in a branch, also called leaves, are colored in orange, and any intermediate or internal vertices are colored blue. There are many applications for DRTs in many fields, ranging from chemistry to biology and linguistics. It turns out that you can also use DRT to model structures in ASIC design and verification. Consider the case of a highly configurable data path unit, which might be part, for example, an image processing pipeline. Such an IP would then consist of a number of primary inputs, which would source data from different points of the pipeline. And the data would typically consist or have different data formats. The unit would then also consist of a number of converter subunits, each of them performing data conversions as the name suggests. The inputs of the converter subunits could come directly from a primary input or from the output for another converter subunit. Additionally, you will have a number of sampler subunits, which performs the primary algorithmic operations in the unit, in the data path unit. The input for sampler subunits would be originating either from a primary input or from the output of a converter subunit. Note that there is additional minor logic in between the modules, pipelining stages, data flow logic, etc., which is represented by these clouds of logic in the drawing. How the primary input converter and sampler units can be connected can then be modeled as a DRT, where the primary input corresponds to the root of the tree, the converter subunits correspond to internal vertices, and the sampler subunits corresponds to leaves in the tree. Also note that there are individual rules, specific rules, of how each of the subunits can connect to other subunits. For example, a particular sampler subunit might only connect to a subset of inputs or converter subunits. Let's look at a particular simple example of a configuration and how we can visualize it as a DRT. Here we have a single primary input source A, enabled, and connected to data converters unit DCY, which performs certain transform and propagates the data to samplers SAMP0 and SAMP1, which sample the data and produce different outputs. In parallel, another sampler procures data from the same source A, producing an additional output. This is a single example of a legal configuration among all the possible combinations. It turns out that the amount of possible configurations, or possible trees, increases exponentially with the amount of available unique vertices. Due to this, and other considerations such as the presence of additional logic in between the subunits, it was assessed that the verification of such a unit was suitable for a constrained random coverage-driven approach. In order to achieve this, we needed an approach to both model and randomize the DRT structure, as well as model the connectivity, the individual rules that govern the connectivity of each individual vertex or subunit. We then identified a number of challenges that we needed to address in order to produce a successful solution. First of all, we should be able to satisfy all the rules that we expressed earlier to produce a valid DRT graph. Additionally, the individual rules that govern how each subunit or vertex can be connected should be able to be expressed in constraints, and this should be done in a concise and maintainable manner. In terms of controllability, we are running constrained random coverage-driven flow, meaning that we will have at the end of our process, we'll have a coverage closure step in which we need to hit certain particular trees or trees with particular properties. So we should be able to steer the randomization to hit certain corner cases or simply direct it to produce a particular kind of tree. In terms of performance, this constraint solver should be able to produce a solution in a reasonable amount of time. And finally, we had a scalability challenge. So the solution should scale well with the amount of vertices in the possible vertices in the tree. Meaning that if for whatever reason we add new vertices to the solution space, the solution should scale well, both in terms of performance and constraint entry. So the solver should still produce a solution in a reasonable amount of time, even if we increase the amount of vertices. And the way we introduce new vertices and constraints should be not mean an explosion of complexity in the constraints. So how hard can it be? We have excellent support from system build language to write constraints. For example, the unique construct, array reduction operators, RunC, and our syntax will generally allow us to come up with neat ways to write constraints. We can also make use of complexity reduction techniques, for example, wrapper classes to encapsulate behaviors and model them. We also have a number of reuse mechanisms available, many presented over years here at DVCon, things like policy classes, engineering constraints, extensions, for example. So with those useful tools in hand, one may be confident, even emboldened, in attempting to model the complete tree structure, both the general DLT rules and the vertex connectivity in a single anatomy, so to say, and then randomize it with a single randomized call, perhaps preceded or followed by procedural code and pre or post-randomize. In this case, one will soon find out that the resulting solution might not meet the mentioned challenges. Perhaps the constraints end up convoluted and cumbersome. Perhaps the performance of the solver is not ideal. Or ultimately, we simply fail to produce a valid DRT structure. So perhaps initially focusing on these existing tools and techniques might blind us from appreciating the big picture, that in particular, we're trying to randomize a tree structure. Consider that a tree has a self-similar shape. The branching points look similar to the root of a smaller subtree. Recursion often deals with self-similarity and problems that can be divided into smaller similar subproblems. In the case of a tree, its root can be analogous to the first call of a recursive function. The branching points are then analogous to recursive cases, and the leaves would be analogous to the base cases where no more recursive calls are made. All these insights led us to develop a recursive backtracking solution, which we'll explore further. In this solution, there were two main components. The first of them is how we model the connectivity of the individual vertices. The second part is a recursive backtracking algorithm that generates a valid DRT structure. Let's start by looking at how we model the legal configuration space of the tree. We can visualize the configuration space as a graph, where each vertex has edges pointing to its possible child vertices. We have a number of source vertices, denoting the primary inputs, and a number of data converter vertices, denoting internal vertices, as well as a number of sampler vertices, denoting the leaf cells of the tree. Additionally, we have a start and a stop vertex, which will not be part of the produced tree, but are rather artifacts using the backtracking algorithm. A possible solution can then be overlaid over the model of the configuration space to visualize the outcome of the tree generation. Note that this outcome corresponds to the example that we previously shown. So, how can we model the configuration space visualized here in constraints? We can make use of a vertex-based class, which amongst other things is parameterized with an ID type, which is generally an enum defining the different available vertices. For each of these vertices, we simply write a constraint listing its possible child vertices. For example, in this case, we have a start vertex, which is always connected to a primary input, a source. Then for each of the sources, we will have a similar constraint listing its possible child vertices. In this case of source A, we have a DCX or DCY, couple of data converters, or it can be connected to some 0, some 1, or some 2, which are the different samplers of leaf cells. We have similar constraints for the other primary inputs and subunit for vertices. Note that the leaf vertices, being endpoints of the tree, can only be connected or have as a child vertex the stop vertex. This set of constraints model the graph that we saw in the previous slide. Let's continue by looking at our recursive backtracking approach to produce a valid DRT given a set of constraints. First of all, what is backtracking? Well, it is an algorithmic technique for solving problems recursively by trying to build a solution incrementally, one piece at a time, removing those solutions that fail to satisfy the constraints of the problem at any point in time. So in the right-hand side of the slides, you can see some pseudocode for what a generic backtracking algorithm would look like. The find function would be initially called on the root of a tree. For the vertex under evaluation, a candidate, we first check a reject or abandon condition, represented by the function abandon. If the candidate vertex fails on this condition, it is pruned from the tree, that is removed from the solution space. If the vertex passes the condition, we must check whether we have reached a leaf cell, illustrated by the leaf function. If so, we return the solution with a function output, generally returning 1. If it's not a leaf vertex, we loop over all the children of the vertex under evaluation and recursively call the function find on them. So, how do we map each of the functions in the pseudocode to randomize a DRT in a constrained random methodology using System Verilog? Well, we make use of a separate allocator class which implements all the different described functions for backtracking. Note that this is a simplification of the solution, and for the full implementation, I will refer you to the paper. Here we have the implementation of the recursive backtracking find method, which we presented in the previous slides. Let's start by looking at the abandon function, which is the condition to check whether the vertex under evaluation does not meet a criteria to be part of the tree. If that is true, then we'll prune the vertex under evaluation from the tree. We do that by adding it to a data structure, a withdrawn queue, which keeps track of all the vertices that should not be part of the or considered in further calls for the find function, and we return 0. Note that the call to randomize has the inline constraint that the randomized child should not be within any member of the withdrawn queue. If we pass the abandon condition, then we should check whether the vertex under evaluation is a leaf vertex. And to do that, we simply check that if the randomized vertex is a stop vertex. Remember, for the modeling of the connectivity, that any leaf cell can only have the stop vertex as a child vertex. If it's a leaf cell, we will add the current vertex to the withdrawn queue, but now for a different reason. It's simply because we have actually reached a leaf cell, we have succeeded and generated a complete branch that will commit to our tree generation. And hence, the current vertex should not be part of any further branches. And we return true. If not a leaf cell, we proceed to recursively call the find function on the randomized children for the current vertex. We do it by allocating the object, we initialize it with the respective IDs, then we tentatively add the current vertex to the withdrawn queue. That is because we shall not use it in the further explorations of this recursive path. We capture the return value of the find function and pop back the current vertex from the withdrawn queue. If and only if we have succeeded in finding a path to a stop vertex, that is, we have randomized a complete branch, then we will add the current vertex to the withdrawn queue, and that will be done. We will commit that, so that will be part in the that will exist for the rest of the recursive calls, and we add the randomized child vertex to the list of children in the current vertex, and we return 1. Note that our generic pseudocode had a for loop here around the recursive part, and that is because that pseudocode was the intent of the pseudocode was to produce a single solution. In our implementation, we are interested in generating a tree structure with several branches. So we'll have a for each loop there, and we'll only stop this recursive process whenever we have randomized. Well, either if we have randomized a configurable number of branches, which is generally a randomizable knob, or we cannot further generate any branch because the constraints in the abandon functions always fail. In many instances, it is much easier to understand concepts provided an example. So I have prepared one to illustrate the tree generation process. In this example, we use the modeling of connectivity that we had shown previously. Before we begin, let's have some explanations about what you will see in the following slides. So any vertex on the randomization will be noted with a blue color. If the randomization in that particular step is successful, then the vertex will be aligned with a green line. If the randomization fails, it will be aligned with a red line. In the case of a successful randomization, we will additionally have the randomized child vertex, which will be colored in orange. We can also see in the bottom of the slide the state of withdrawn queue at that step, and the constraints that applies to the vertex under randomization. We then begin by calling the find function on the start vertex. Note that the state of the withdrawn queue is empty at the step. We're starting the process now, and that the start vertex can only have a child, a primary input, source A, source B, source C, or source D. In this case, the constraint solver has selected the source A as a child to the start vertex. We continue our process, and now we randomize the source A vertex. Note that we have put the source A in the withdrawn queue, and it is in italics. That's to denote that this is not fully committed. We will only commit vertex to the withdrawn queue when we have produced a complete branch. We can see the possible children for the source A listed in this constraint. In this iteration, the solver chooses the DCY vertex as a child to the source A. Continue the process. Now DCY is under randomization, and the solver chooses the SAMP 0 for the DCY. Again, note the updated state of the withdrawn queue. Now we have reached a leaf cell. We have the SAMP 0 that is being randomized, and it produces the stop vertex as a child. And we update the withdrawn queue. Now let's see what happens in the next iteration. Since we have produced a complete branch, then we go back one step to the previous vertex, and we randomize it again. Note that the three vertices in the withdrawn queue are not in italic anymore. That is because we have produced a complete branch, and that is now part of the tree, and we commit this member to the withdrawn queue. In this instance of randomization, now we have the DCX vertex randomized as child for DCY. We then proceed to randomize the DCX vertex. And now we can see that something interesting has happened. The randomization has failed. That is because the DCX vertex has as possible children only the DCY and some zero vertex, both of which are part of the withdrawn queue. So that we cannot produce a child for DCX in this instance. We then must backtrack back to the DCY vertex to continue further exploration. We do that and randomize a new child vertex for the DCY vertex. Note that the DCX vertex is not part of the withdrawn queue, so the solver could not have picked that again. We continue the process of randomization, producing different branches, backtracking, and producing more branches until we eventually reach the start vertex or generate a configure number of branches. We have now reached the start vertex and produced our first tree. This is the same tree that we have seen in previous examples. We have shown now the two different aspects of our tree generation scheme. First one, how we model the connectivity of the individual vertices, and the second part, the recursive backtracking algorithm that produces a valid DRT structure given a set of constraints. So how did we fare against our previous defined criteria, those challenges that we presented in previous slides? In terms of validity, well, this is really given by the infrastructure and proven over the course of a number of basic projects where we successfully closed the defined coverage. In terms of controllability, it's rather straightforward to direct the framework to produce solutions in certain regions of the solution space. On the right-hand side of the slide, you can see an example where we subclass the vertex class, which has all the base legality constraints, with a sample zero subclass, which has additional constraints that would force the constraints or the framework to produce a tree having always the sample zero as part of the branch. Note that you can always also steer the randomization using the distribution operator, the system Verilog distribution operator, to produce to make it more likely to produce solutions in certain regions of the solution space. In terms of performance, we measure the time spent of the constraint solver for the number of vertices that we use in our actual design that we're verifying. And we measure that time was within the boundaries of test benches of similar nature, similar complexity. We also created a simple scalable UVM environment, in which we could configure a number of available vertices for randomization. You can see that in the graph to the right-hand side, and we ran hundreds of simulations for each data point. What we noticed was that the solution, our framework, had a polynomial time complexity, which is a tractable result for this kind of problem. In summary, today we have shown you the two different parts of our solution to produce a DRT. The first part, how we model the connectivity of the individual vertices. We then showed you the second part, how we use a recursive backtracking algorithm that, given the connectivity specification to constraints, produces a valid DRT structure. We discussed a bit about how our solution fared against our previously defined criteria or challenges. Finally, I want to mention that this is a generic UVM framework that could be used for any application that requires to randomize a DRT structure. I would like to close the presentation by having a second look at the picture of the climbing tree. In the background, we have a forest of trees. The attentive listener might have noticed in our example of the tree generation that once we reached the start vertex, there was nothing preventing us from randomizing a new child for the start vertex, that is, randomizing a new tree. Our flow is capable of generating multiple trees if the application requires it. So with that, I conclude the presentation. I want to thank you and wish you have a nice day.